Anyway, so that's fine. So the general characteristics of the major fuel cell types, and this is something I think when we give you the slides, which I will give today, this is the one that I would like you to remember, because the reactions, etc., you can find it. So the operating temperatures really is very, very important, and then also looking at the electrical efficiency. That's also another important thing. And under the SOFC, solid oxide fuel cell, oh, by the way, the first one is the alcohol fuel cell, which could be methanol fuel cell or ethanol fuel cell. PMFC we know, PAFC is the phosphoric acid fuel cell, molten carbonate, solid oxide. These are all electrolytes. Okay. And then direct carbon means directly carbon pooling. So that depends on the depends on the planar. So the planar and tubular, that's what I was going to tell you. The planar means the different stacks. They are one by one, one by one, one by one. They are connected all in series. Okay. Very easy. Simple. I mean, it's simple actually. The problem is that to maintain the sealing for the planar thing, as we were discussing, having a square cross section or rectangular other than circular cross section in a high temperature environment, the sealing is a big problem. So that has limited to some extent the planar cells development. So if you're thinking of digressing a bit, if you're thinking of making a rectangular one, drop that idea. Run away from it. Sorry? Yeah. So the tubulars are now pretty well developed, actually. Correct. Yeah. So no, not necessarily. I mean, it depends on the size of the tubular oxide fuel cells. The sizes can be made anything. Now you can get them in the tubular mode, single unit 1 megawatt. So the designs are coming up. So if there is more of a demand, I'm pretty sure that they will become larger and larger. Yeah, it's a good idea, very good idea, because then you are moving away from the thermodynamic limits for the gas turbine and then getting extra from the solid oxide, from the electrochemical conversion. Close to 60%, surely. Yeah, very good thermochemical electric. I think it's still the fuel cells are not to the size as the gas turbine. So gas turbines are very large. It can be used as a distributed. I think someone has to make the move and then get it done, because there is no reason why it cannot be done. Yeah. I don't think there is much to be demonstrated, frankly speaking. It can work. The thing is whether if it is built at a place where you have good supply of, say, solar energy that gives you the hydrogen, and you are not requiring much of a water supply. So in some of the desert areas where electricity transmission lines, the conventional electricity transmission lines are not all that have not penetrated, those are the areas where you can go. And the local rural electrification is a classic example where it can be done. It just needs the willpower on the farm, on the part of whoever the power generating companies or the owners of the power generating companies are. But there is absolutely very little which is risky in that. Yeah. Well, I think even the first one doesn't need to be maximized. The first one can be just the demonstration that look here we are not relying on the grid anymore. Here we are relying on our local fuel coming from. Technically, the possibilities are endless, really. So every situation will be different, and it can be done. So let's go into it again. The internal reforming, that's also I wanted to bring your attention to. The first few generation of fuel cells is not possible. But you see the molten carbonate fuel cell, the solid oxide fuel cells, as soon as you started going into the higher temperature area, you are having designs available now where in situ internal reforming of the methane is possible with catalyst. And that's the other beauty of it, that rather than reforming it outside, where yesterday we saw that the conventional steam reforming or conventional CO2 reforming do need about 900 degrees or so. Here in a compact manner with the help of particular catalysts, and some of the catalysts we will see later on, you can actually do it at the fully fluid fuel cells operating temperatures, 650, 700 degrees. So as soon as the point I'm trying to make is that as soon as you go towards the higher temperature fuel cells, which MCFC onwards, then they open up the possibilities for accepting new fuel other than just hydrogen, and also reforming in situ, and also the ability to go higher up in the size. Then and the other one is that the third from the bottom, the startup and the shutdown time. Obviously, the larger you get, you will need longer startup and longer shutdown time. But this is of the range of hours, 3-4 hours, really doesn't matter. And if it is distributed generation, if you are running it at part load, then it's not a problem. You can do it. It will not be able to follow the load. That means they will never be able to be connected to the industry's requirements. But for distributed generation, where part load operation or load following is not a need, these things can work. So, and if you look at the footnotes under this table, some small tubular design units may heat up to the operating temperature in less than 1 hour, and I have seen large units heating up in 2-3 hours at most. So a lot of advances are actually being made and still being made, because everywhere now these manufacturers in Japan, in China, in US, in North America, they see that as the electrolysis become more and more widespread, even ammonia becomes a fuel of choice which can be transported. Methanol becomes a fuel of choice which can be generated in one place and then can be transported to another place. Methanol can be very, very cheap. Methanol, as you know, we heard yesterday, the methanol price is very, very low. So methanol can be reformed, or for that matter, it can be used in some of these types of fuel cells as well. So let's go now to the next bit. the AFC, the alkaline fuel cell. These are the point I note is that these are the earliest fuel cell systems that were developed. And those are mainly developed by the US for their space missions. Electrolyte is the alkaline hydroxides, and the concentration of the hydroxides solution, that means the electrolyte solution, is about 35, anywhere between 35 to 85 weight percent, rest being water. Operating temperatures 80 to 250 degrees Celsius, do not require precious metal catalysts, and nickel is commonly used as an electrode material. But the major the drawback is the alkaline fuel cells, significant degradation when exposed to CO2. So can anyone tell why? Potassium carbonate will be forming at those sort of temperatures. So if you have lots of carbon dioxide, then this is not the way to go. But the performance loss and long-term durability of the alkaline fuel cells are still the major issues. But then again, at the on the same token, you have to really be thinking, am I looking for 8,760 hours of operation from this or not? If not, then who cares? If you want to operate it for 12 hours a day, then the longer time durability for continuous operation will be lesser of an issue. So these are some of the pluses, but this is very well developed, very well developed. Then you have the other one is the membrane here, or the electrolyte here, is actually a polymeric membrane, so through which the electron transfer takes place. And the Nevian filters. Has anyone used the Nevian filters? Nevian filters are polymer membranes. If you buy a gas chromatograph, when a reputable manufacturer, then they will ask you to install a Nevian filter at the inlet to the gas chromatograph in order to clean up a lot of gases, moisture, in order to clean up the particles. So that's Nevian. Nevian is cheap, readily available. You can make your own Nevian filter if you want to make it. But anyway, that's used, and it's a highly proton conducting. So that's an ideal material. And the anode and the cathode materials are typically finely divided platinum supported on high surface area carbon. It's essentially strong charcoal with carbon baking paper and or cloth as gas diffusion layers on both air and fuel sides. So where in the fuel cell, closer to which electrode do you supply the fuel? Cathode? Not cathode? I thought it's cathode, no? Cathode? Anyone for cathode? No one for cathode, okay. That means it is anode. Okay. Oh. So I should have put that blank. Sometimes I do that. Did not get the time to become tricky. Next time. Typical fuel cell operating temperature is very low, and 10 kilowatt for stationary applications you can buy them, and 50 to 200 kilowatt for transportable units. You can actually buy them now. PEM fuel cells are many manufacturers. I think if you have a little bit of a courage, form a startup and start selling fuel cell. Just buy few, get some experience, develop your own. You are all engineers, chemical, mechanical, etc. Why go and go into academia? do something for the society. Which fuel cell? So you can decide. I think don't go for the SOFC or MCFC. You will not win against the multinationals, but the lower ones. The cheaper. You know, the PEM fuel cell. Literally, I saw in the eBay it's about $29 selling. Now. eBay always doesn't sell second hand. But the point I make is it is possible. Huh? Well, you can just have the metal hydride as the hydrogen storage, and then have a small, reformer in your manufacturing facility. Supply those ones, sell them, and ask the customers to bring back their anhydride. You recharge them, give them back, let them put that in their fuel cell. It's a businesses. Think of that. CFD models and other things you will do all your life, but that's fine. This is also good. Yeah? But the number of academic jobs are decreasing. That's also a fact. Maybe true in there. I think if they make a rule that I think you should all make a rule that for the first 5 years after graduation, you are banned from coming to academia, go and practice in industry, then come back. The majority of them will not come back. When this will inflate, they will not come. They will learn a lot. But I can tell you, honestly, I am saying, fuel cell is area, particularly in India, it could be a booming market. This is one, and the other one is waste processing, waste plastics processing. If you want to know a bit more about that, talk to me, and then I'm talking to a few people. I'm just freely giving them the service, and they are. Huh? Yeah. Yep. So. Yeah, I know. So you can all become Gujarati. There's nothing. Plus, you now have PhD. A lot of knowledge, right? Go for it. So I will be getting their email addresses, right? Yeah. Okay. So I'll be from time to time. I'll be asking you how far you are from your PhD, and what exactly are you planning to do after your PhD. That's the first thing I ask my PhD students when they come in. And they said, "Oh, I'm not sure." And as soon as I hear, if not sure, it's a good idea. That's not a problem. But if they say, "No, I want to become an academic," what? Become an academic? What? You haven't practiced your engineering. All you have done is you have done your undergraduate degree, you have master's degree, you have done your PhD degree, and you haven't gone away from this room. So to go and flick some valves, break few pressure transducers, and then you learn, and then you come back more confident, and that's fine. Okay. Anyway, so this hydrogen fuel cells. These are 1 to 2 watt levels. This is another classic example. They are for portable powers, and you go into your expeditions and take some of those. 1 to 500 watt available sizes are available. Last time I saw whether any Indian company is manufacturing or not, I could not find anything. So maybe some of you will be the first ones to do it. And you are doing all enhanced heat transfer, right? So just to enhance fuel cell utilization efficiency, go for it. And you can acknowledge me for encouraging you to taking that entrepreneurial path. I'll be quite happy to mentor. Yes, that's right. See, metal hydride-based high energy density energy hydrogen storage, you can buy them. So all it needs is somewhere hydrogen production facility, and you are not looking at million meter cube per hour. You're looking at a lot less. You have access to natural gas. You have access to a reformer. Produce the hydrogen, store just design few cells where you will be charging your metal anhydrides, which will go into your fuel cell that you will be selling. So there are some available for 10 minutes storage time. You can easily sell something which 30, 40, 1 hour storage time. But these are fantastic things. Okay, then the methanol and the ethanol fuel cells. The electrolyte is still PEM, as we mentioned before. Fuel is different. Methanol is very cheap. Ethanol is another one, and sluggish. But the problem, one of the problems still to be overcome, is that the electrochemicals, chemical reactions involving the methanol and the steam is still a bit sluggish. But there are a lot of developments that are taking place in that area. The other one, liquid ethanol, is ethanol can come from all sorts of agricultural sources. They are made. You don't have to reinvent that wheel, and is oxidized at the anode in the presence of water. And even though they are early stages of development, but they can be developed very, very quickly. As soon as you have few of those running in your backyard, you can easily do those. So the point I'm trying to make is that the fuel cells opens up so many possibilities. Not only that you will have to rely on just hydrogen, it can be a local fuel, locally available fuel. Sometimes even the biodiesel can be a fuel, even though I haven't seen anything, people even thinking of it. Biodiesel sells about 50 rupees, 100 rupees a kilogram. No one wants to use it. But you can make so many things from the glycerol. The glycerol is the byproduct from the biodiesel production. So biodiesel is used, but glycerol no one wants to use it. I mean, simply because it's plentiful, and therefore the cost is low. And anything which is low price, we don't buy it. That's the human psychology. If you have 2 bottles of water, the higher priced one is the one that we always go for. Unless you are a stingy person as I am, you buy only the cheaper one all the time. Yeah, that's right. Glycerol is hydrocarbon, and glycerol can be converted to hydrogen. Easy. So open up a project from the biodiesel. I can tell you, I don't know how big the biodiesel industry is in here. If you go to Brazil and look at the suppliers on the eBay of glycerol supplier, glycerol is $1 to $2 per kilogram. But glycerol is hydrocarbon, and glycerol is ripe for reforming. Maybe you can do that reforming in your fluidized bed. Seriously. And get hydrogen. Generate that information. Then patent it. Keep my name as one of the authors. If you're doing it with steam, no. Not monoxide. Yeah, it remains to be seen. I mean, it remains to be seen. I've asked one of my students to do that when she comes back from overseas, but it can be done, easily done. So the hydrogen can be sent towards one way, and if you have carbon dioxide and carbon monoxide available from other sources, then you can think of combining into a reaction and then get whatever product you want to get. So So the direct methanol fuel cell and direct ethanol fuel cell, these are still low temperature, but one of the beauty is that for ethanol, the energy density is much higher compared to methanol. Both of them are cheap. Phosphoric acid fuel cell, concentrated phosphoric acid electrolyte. I'm not sure exactly why they started it, what is the rationale behind it, but having it there, it makes sense for me to bring it to your attention. The phosphoric acid, by the way, is a very good homogeneous acid catalyst for homogeneous reactions. This is one of the very well-performing catalysts. And it's not surprising that it's also a very good electrolyte. So the anode and the cathode are carbon-supported platinum metal catalyst with an average loading of around 0.2 to 0.3 milligram per centimeter square. The temperature needed, which is as an engineer we need to know, is about 200 to 215 degrees Celsius because it's limited by the vaporization temperature of the phosphoric acid. But 200 kilowatt to 1 megawatt sizes are available. Then comes those big heavy hitters, molten carbonate fuel cell, solid oxide fuel cell, and direct carbon fuel cell. We'll come to that. So in the molten carbonate fuel cell, as the name suggests, the molten carbonates are the electrolytes. Okay? So those can be potassium carbonate, it can be lithium carbonate, or sodium carbonate. And so they have to be held in a porous ceramic matrix or tile as they are used as an electrolyte. 600-650 degrees centigrade is the operating range of the molten carbonate fuel cell, but depending on the special carbonates being developed similar to special amines being developed in CO2 capture. Special carbonates being developed which will take them to the higher temperature. Whether you need that, that's another story, because you have much better higher temperature fuel cells available, such as SOFC and DCFC, etc. So these are available up to 1 megawatt, but I have seen Westinghouse's, Siemens, offering of 2 megawatt unit as well, single unit, so quite large. Porous ceramic matrix made from lithium aluminate is a few hundred microns thick and is fabricated via tape casting. So the reason I wanted to have this one is that sometimes you may think that these are very difficult to make. And as we saw in the table, internal reforming within the fuel stack is possible, provided you get supply of steam. Hydrogen and CO produced are electrochemically consumed. The water vapor formed in the anode chamber is utilized in the reform reaction. And reforming of natural gas is at lower temperature, 650 degrees centigrade, than at external reforming that we know of that requires 900 degrees centigrade. So one of the reasons is that you can also put in with ceramics being the material of choice, you can also put in the catalyst, nickel or platinum, which will be more recoverable from these carbonates when they are bounded by ceramics. So there is no chance of retrieving them. Chances of retrieving them is a lot easier. So it's not like the catalyst getting lost in a matrix of ash. It's not like that. Okay. So that possibility actually allows the reforming in situ of the natural gas to take place at lower temperature, about 650 or so. Ideally, if you recall yesterday when we were discussing about natural gas reforming, methane reforming with either steam or CO2, we are looking at 900 degrees, right? magnesium aluminate, lithium magnesium aluminate, and all those kinds of nickel magnesium aluminate. So essentially the similar type of compounds of the elements from the similar areas in the periodic table that you will be using as the catalysts here. So the molten carbon fuel cell. Then let's go to the solid carbon fuel cell. These are the electrolyte is an oxygen ion conducting, and it can be tens of microns thick, so 40, 50, 100 micron thick, and could be partially or fully stabilized zirconia doped with a certain amount of yttrium oxide, which gives the zirconia a much better conductivity, ionic conductivity. The anode generally is a nickel yttrium stabilized zirconia. YSZ stands for yttrium stabilized zirconia. And the cathode is a ceramic composite, usually comprising of the electrolyte material and doped with what we call typically as LSM. It's a compound of lanthanum, strontium, and manganese oxide. Huh? What is doping? So, what is doping? What is doping? Huh? Why amalgam? Amalgam is different. So all the examples that you have given, these are all valid. The other one is in the catalysis area. So you have a ceria, say, as the support material, you dope it with nickel or indium or ruthenium, whatever you think is a good catalytic. So doping means adding a little bit of it into a larger base. That's what doping is. Okay. So we have found this out. So the solid oxide fuel cells typically 800 to 1000 degrees, and therefore that basically means majority of the fuel cell stack is made up of ceramics. And there lies a challenge. The challenge is you can make this what's a fuel cell stack? The fuel cell stack means you can make several fuel cells stack one over the other, so that you can have a larger one rather than many small ones. So if these are of planar nature, and by default you will need ceramics because of the high temperature, planar, then it's very difficult to ensure the sealing, right? But if you can make it with ceramic tubes are available. You can cast ceramics into tubes. In that case, you can make the tubular reactor, and those will be a lot more stable, sealing-wise. So that's the point that I made here, that planar design, stacks connected in series, and sealing is an issue. Tubular cells, lesser of an issue. But amongst all of the fuel cells, I would say that solid oxide fuel cell is the most developed. There are many suppliers, as I said, the GE, the Fuji Electric, the Mitsubishi Electric, you name them. And there are enormous number of Chinese, cheaper Chinese suppliers coming into the market as well. And so that's it. So that then, any question on solid oxide fuel cell before we slowly move to DBFC and then DCFC? So the DBFC, let's take it first. Here, Of course, the hydrogen is fuel, but the hydrogen is actually stored inside sodium borohydride. So that's where the letter B comes from. This gives, these are very good, storage adapters of hydrogen, not to the same extent as palladium is, but very good amount of hydrogen that can be stored by the sodium borohydride. The power density is up to 290 milliwatt per centimeter squares is available, and with air as the oxidant, but with hydrogen peroxide as the oxidant, you can get about 600 milliwatt per centimeter square. So you get a lot higher the power density with the hydrogen peroxide as the oxidant. What's the power density? Why power density is important? To answer it, look at its unit. That will tell you immediately why it is important. Correct. So it will make it more compact. So one of the races going on for amongst the different developers is go higher and higher and higher and higher with respect to power density, because then it will make it so much smaller. You can pack so much more power in the same volume. But one of the problems is that with this particular one is that there are lack of suitable catalysts for efficient electro-oxidation of the fuel and electroreduction of the oxidant and high cost of sodium borohydride. But then you can also think of, by looking at the periodic table, is there any other formulation that I can make as a strong but cheaper the hydrogen storage material. And the only thing that your starting point will always be at the periodic table. Right? So, you go to 12:55, so around 12:50, okay. So we'll finish as much as possible. Then fuels for fuel cells. This is what Dr. Dave asked right at the beginning. So here is one slide, but we have discussed it already. With the exception of direct alcohol, that means the AFC, and the direct borohydride fuel cell, which means the DBFC, which we just discussed, all commercial and near commercial fuel cells operate on pure hydrogen or a mixture of hydrogen and CO. So it's only the higher temperature ones which can tolerate CO. The lower temperature ones, higher temperature ones means MCFC onwards. The lower temperature ones cannot tolerate CO. So how is it then hydrogen then made? It can be made from different sources, different ways. External reforming is one way if you have plenty of space, etc. Internal reforming is one possibility that is practiced, or the partial oxidation of the carbonaceous fuels. So that one is mainly for hydrocarbons. So partial oxidation is nothing but a sort of gasification, really. And reforming. So partial oxidation is nothing but reforming. Partial oxidation is nothing but gasification. It's just a name. It's just because you are reforming it with oxygen as opposed to reforming it with steam or carbon dioxide. That's why the partial oxidation term comes in. Okay. Correct. So essentially, you can argue that my electrolysis or solar-assisted electrolysis is free of energy, certain times of the day, certain times of the year, right? And it's a storage. So that hydrogen, you put it to your fuel cell. Essentially, you can argue that I am getting emission-free hydrogen at practically. Yes. Yeah. So the batteries, so the battery sellers, you are actually not competing with them. You can tell them that, look, you are complementing. I'm generating the power for you, and you are just storing it. So we are not trying to break your business model. Conjugate, yeah. Correct. Batteries. That's right. So I think Madhu will start that. She's getting excited. She's moving, rocking. So she's getting excited hearing that. You should really think of it. You know. You are working all on enhancement of heat transfer. So in the fuel cell, enhancement of ionic transfer is not dissimilar to enhancement of heat transfer that you are doing. So you have to think of, yeah. So think of that. Just a natural progression, I think. It's called POX. So what is the problem? More efficient. Yeah. So okay. Why, as I said, why we are calling it partial oxidation? Because reforming always means either reforming with steam or reforming with CO2. So you are not bringing in any oxygen molecule there, oxygen atom there to break the bond and then have an oxygenate. So technically, similar to the concept that you can break the tar by steam or oxygen, you can break these hydrocarbons into smaller molecules. Hydrogen is one by oxygen. That's why it is. So it is reforming in one sense, but it is reforming with oxygen. Someone gave it the name partial oxidation, and then it just continued. It's the same. Okay, so yeah. So then the 1, 2, 3. Third bullet point: relatively pure hydrogen is required, but up to 20 ppm CO and less than 1% CO for PEM. The phosphoric acid fuel cells are tolerated. So it's still a very low level of CO that we are talking about. So that's why I say that some upstream gas cleanup may be necessary. And the other point, the 3 bullet points I have clubbed together, as you can see, SOFC and MCFC with hydrogen and CO with internal steam reforming. They allow internal steam reforming, these two. Hydrogen can also come from electrolysis of water. That's the other point that we'll make. It's related. And then the high temperature ones are less prone to poisoning. Poisoning by those trace gases, poisonous gases. It can tolerate a lot. Five, 6% CO, not a problem, because you have the internal reformer. Put the steam into it, CO goes towards what? If you reform CO with water vapor, what will happen? So you get hydrogen, essentially the fuel cell. The only problem is the temperature is too high to go into that direction. Because for shifting, you need less temperature, lower temperature. So it is too high a temperature. But then that's a design issue. Okay, then, so where are the fuel cell applications? Fuel cell applications are everywhere. So that's why I'm encouraging you to become an entrepreneur. Because you see everywhere you can put them, right? So immediately after, towards the end of your PhD, start thinking of business, applying your PhD knowledge. Why are you smiling, laughing? It is very widespread entrepreneurship after PhD. Because it's so, yeah? So, it's becoming. See, Australia is slightly larger in size than India, but we have only 24 million people. The middle part is all desert. So this let's keep this slide for some time, so that we can encourage you into becoming, serious thinkers in. So what will be the safety issue you can think of? Yeah? What fuel is used for cooking at your home? Huh? At your home, has any explosion ever taken place? Anyone's kitchen? Anyone's kitchen explosion ever taken place? So the point I'm making is that in as much as you should know that this is a possibility, you should also take solace in the fact that this can be a problem which can be easily engineered out, because almost every household in the metropolitan cities here have highly explosive, highly flammable, highly combustible gas closer to a source of ignition. But you are all alive, you are thriving. Right? No. So the laptop battery is recharging. So you go for a expedition in the desert or somewhere else. You carry your fuel cell, where you won't be getting the electricity supply board will not be sending you the electricity. You take your electricity. What's up? If I can get one person become entrepreneur after this, after then I'll be feeling very happy. I think you all have your cocoon of comfort zone, which you don't want to break through. Have you seen the hatcheries for crocodiles? From the eggs, how the tiny crocodiles, at what speed they come out? Have you seen that? You go look at it at YouTube, you'll find it. That's the speed that you have to break out. Huh? And you can change it. Everyone gets married. Who doesn't get married?
I think that's exactly means the second question.
Yeah. Yeah. So choose as your partner who can be your partner at crime, which means equally entrepreneur. Just do something, and you can do. So DCFC, very quickly. So as the name suggests, it is direct carbon. Okay, so that means no hydrogen business. Carbon is coming directly into it. So let's see what it is. Essentially it is similar to SOFC, or molten carbonate fuel cell. Only difference is, the major difference is that rather than being fed gas or liquid fuel streams, the anode chamber is supplied with a solid fuel. So we know solid fuels have to go into the fuel has to go to the anode, and you are just supplying somehow the solid fuels to come in contact with the anode surface. Otherwise the anode surface will still be the same. Or in fact, the carbon itself can be anode if you have prepared it accordingly. Yeah, correct. So for the fuel cell to operate at its maximum efficiency, these are the cell reactions. So that's easy. What reactions takes place at the anode? What reaction take place at the cathode? That's what I have written. So at the anode, it's the carbon which gets oxidized. At the cathode, the oxygen transfers to the ions, and then electricity flows. As simple as that. So the principle is very, very well known. We don't have to. So let's see the different variants of direct carbon fuel cell that different groups are working in different parts of the world. So we have the anode on one side, close together with the fuel. And then we have the cathode on the other side, and in between we have the electrolyte. So let's focus on the electrolyte first. The electrolytes are not any different from what we have discussed so far. This can be the molten hydroxides, so potassium hydroxides, etc. Or it can be the molten carbonates. Potassium carbonate could be one. Or in this case, the different concepts with different types of fuels and contacting mode. I will come to that. The electrolytes are all ceramic electrolyte because temperature is high, has to be high. Therefore you cannot afford to have an electrolyte which can degrade at low temperature. Okay. Now let's look at the anode side together with the fuel. So the anode side, in one variation, the first one, it can be the solid graphite rod as fuel, and of course that can be anode as well. Graphite is something which you cannot convert thermochemically, right? Very, very difficult unless you go to extremely high temperature. Electrochemical conversion, easier. Okay. And that's the reaction that has been shown there. Then the next row, you have the carbon particles as fuel in molten carbonate and anode. So you are no longer giving the carbon as solid rod, you are giving it as discrete particles. Okay. Then in the last row, there are different concepts people have been working, and I will see some of the schematics later on. One is that it is the contacting of the carbon and the anode which is the key, right? If the contact is not good, then you will be having tremendous anodic resistance, fuel utilization factor will drop, your efficiency will drop. Okay, so from that point of view, we know that fluidized beds give a good contact between two different mediums. So here one is a anode surface, and then you are keeping the carbon particles that you are giving well fluidized so that they remain in contact with the anode surface all the time. So that's the concept it came from. But it derived from standard chemical reaction engineering, the fluidized bed. Well, yes, can be. If you are not careful, absolutely it is possible. If you think that we will be converting it 100% electrochemically, then you will give it, fluidize it with nitrogen, for example, so that it's inert. But if you think that, look, I won't be able to convert it 100% electrochemically, or it will take very, very long time, needs to be seen, still needs to be seen, then you can decide that, look, I will do both simultaneously. Convert some electrochemically, convert some parts thermochemically. Okay? So in one of the slides, I think I forgot to mention that heat generation. It's a yes, that's right. So once you have started it up, it's not a problem. It will be more or less self-sustaining. That should be there. Correct. Startup has to be there in anything, any reaction that you get going. But of course, thermochemical reactions take a higher temperature to start. Electrochemical, less. It's just the potential that you need to create. Then the second row in that concept 2, as they call it, it's the molten tin. In the molten tin anode, you are putting the carbon. Okay. And then in the last one, you have the molten salt, and the molten salt could be lithium carbonate, for example. Lithium is one of the most abundant material that you can get. So lithium carbonate is not very expensive either. So these are different ways of bringing the carbon into the DCFC. So let's then go into the next bit. Inside the anode chamber, a combination of direct and indirect carbon oxidation reactions can occur. The carbon particles which make direct contact with the electrode can react with the oxygen ion and are converted to CO2 via this particular reaction, which is simple reaction really. And then the carbon particles which do not make direct contact, there will be some, they also have their chance. They are oxidized by this particular reaction, okay, which is a standard chemical reaction. So it's the C plus CO2 boudoir, and then you have it this way. So this is the beauty of the DCFC, because technically you can get the best of both the worlds, both thermochemical and then electrochemical. So there are few types of DCFCs that are under development under the main heading of DCFC right at the top. You have the second layer is different types of electrolytes, which we have mentioned. And for the different types of electrolytes, take for the solid electrolytes, you then have the different media. So the solid electrolyte can be the solid carbon, it can be the molten carbonate, it can be the molten metal. And then under each of those, say let's first go to solid carbon, the direct contact can be created by fluidized bed. or you can decide that no, if I will be too difficult, I will gasify it outside. I will have a small gasifier next to my fuel cell and bring the gas that way. That's also being investigated. Easier said than done. Or gasifying in situ, inside it. Gasifying the carbon in situ. Very, very challenging. And then under the other side, under the molten metal media, you have the indirect metal oxidizing because the carbon coming in. So inside the molten metal, it will get reduced or oxidized depending on how long and how much oxygen it can come into contact with. Okay. So these are the different ones, and let's take some a few sketches. We should be finishing soon. So this is the one that is being investigated by a company in US. They're also front runner, Sarah. And here, carbon acts as both anode and fuel, and then cathode is whatever. We have seen all sorts of possibilities. Air is brought in the way that they have. So it's actually now starting to show the actual configuration of it. So we have so far just talked about the concept. So now I am showing you a few of the figures wherein how people are actually doing it. Okay, and from this we can do. You can measure a few things. So all they do is through the impedance spectroscopy is very well known in electrochemistry. You can measure certain things. You can measure the voltage. You can measure the current. You know over what surface area this has been generated. So you can plot everything that is needed to be plotted for characterizing the performance of a fuel cell, which are power density, current density, cell open voltage. Okay, these three, right? We have seen that before. And of course, behind all of this is the fuel utilization factor. How much fuel remains unutilized? That's something also you can find. So that's one configuration. Then this is the configuration investigated at the LLNL. LLNL is the Lawrence Livermore National Lab in the US. There you can see, so it's a separate container, if you like. You have an alumina tube which can take withstand high temperature. The carbon is filled this way here. Carbon is filled this way in here, and the carbon goes directly onto the anode collector and gets converted, and then you have the oxidant coming from the side and going in there. So this is another design that Lawrence Livermore came up with. And there are variants of this ones being floating now in the literature. People are doing it all in a different ways, but essentially centering around that. So again, how you will design it, it's entirely up to you, right? Keeping in mind that ensuring a good contact with the anode is the key, and that you really need to have an environment to supply the oxidant to the cathode so that the ions can be transported. Within those two major requirements, you can do whatever you want to do, whatever you think is the easiest to do. And then we are almost there, and exactly the same type of measurements, these three things that people will measure and then plot and then find out how this performance of this particular configuration stacks against the other ones. That means how the performance from my design, because these are only three measurements that you are doing majorly, compares against the performance of the other designs or other types of fuel cells. Then the last one that I wanted to show you is this one. This is also from Lawrence Livermore, and they have the in situ pyrolysis that they are talking about. So if you look at the green fuel that is produced, that is fed. Green fuel could be biomass. Right at the top, that green horizontal block, and the heat coming from the bottom of the fuel cell is actually pyrolyzing, and that's dropping the carbon, which is called charged fuel, into the anodes. Okay, and where is that devolatilized pyrolysis gas going? They are collecting it. So they are saying that this is another design where from I will be using the biomass as it is without any pre-preparation. For example, I will collect the calorific value of the gas, and then I will get also the char to come in contact with the anode. I will distribute the air in the way that I have shown, and the rest is simple. So this is another design, and the second one at the bottom is also another design. So only difference here is that you are integrating pyrolysis, taking the volatiles away, and hopefully some of the pollutants away there as well, leaving the char behind. Okay, and then this is the one design from GE. So this is a strong player. There is the pyrolytic carbon anode cell. Here the carbon is the pyrolytic carbon. The char is the anode, and the electrolyzed is stabilized zirconia, whether it is stabilized with yttrium, YSZ, or anything else, doesn't matter, but it is stabilized zirconia. And then the anode, as I said, is the pyrolytic carbon in the middle, and the cathode is the molten silver. And everything is inside a ceramic tube because it all has to be high, high temperature. Only thing is, it is also direct carbon, but it is not direct solid carbon. It's the direct carbon coming from the natural gas. Okay, so this is another variant. So most important thing that I want to bring to your attention is that in any fuel cell, this direct fuel cell, there are three things very, very important, and this is called the concept-wise. It's called the triple phase boundary, and do remember it. You will hear it if you follow that literature quite a lot. That triple phase boundary means, as it is shown in here, in one area you have the carbon contacting with the anode. In another part of that triangle, you have the electrolyte, and through the electrolyte the oxygen transport is important. Through the carbon current anode, that interface, supply of the carbon and the electrical path for the conduction of the electron is important. And at the end of the day, you will have to take the product gas out, which is the CO2 from here. So this is called the triple phase boundary. That means the boundary is defined by electrolyte, carbon anode, and the products. So you will hear it quite a lot. That's something that I would like you to remember a little bit if you can. And then this one is another design. This is a very fundamental piece of work, and so that's why I have written here fundamental investigation. What they do is you can actually make a cell just like a button. Just you have those button cells for your watch and etc. These are button cells. So it is the electrolyte, anode, and the cathode squeezed, made there, and then the anode can be carbon, and then do the test. The beauty of this type of test is that these are all highly PhD oriented work, because they give very good quality data, and you can actually generate significant amount of fundamental information which will be difficult to generate from the other ones. the big one, the bigger ones, as we showed in here. These are the ones. So you can actually see who is doing the scaling up and who is doing the fundamental work. Fundamental works are done by the university people. There is a room for it, need for it, and that's what we'll be doing. So the principle is the same, and then the others as well are doing in small, fuel cell. That one of my students is currently working on this type of fuel cell. The previous one worked with button cell. But the point I'm trying to make is that it will still give you fundamental information. Once you are done with the button cell experiments, then you move to slightly larger scale, similar to the gasification research that you do. If you go by step, chemical looping or gasification or whatever, you do it exactly that way. So that's how the fundamental work. And this takes me to the last slide. Where is DCFC? We still need to know a lot. Longer term operation of a DCFC of any design has not yet been conducted. Which is the best design is yet to be seen. So we really are looking forward to learning a lot. But the experiments are not too difficult. But it could be absolutely a gold field of information that you can generate. It's a fantastic research area together with the chemical looping. So that's the reason that I discussed this towards the end. Gasification is saturated. You need to know that understanding of it to carry forward the other work that you would be doing. But in the chemical looping area, for all sorts of applications, fuel cells, all sorts of applications, there's an enormous amount of fundamental work leading to the scaling up that can be done and is necessary. So that's the current status. So that's basically it. I'm not sure, are we coming back after lunch? I am finished. I don't think so. So if I don't see you after lunch, then have a good time with your career, and always think yourself that look, as you are doing your postgraduate studies, master's or PhD, you are on a mission. Okay, the earlier, the quicker you complete that mission with some very productive output, the better it is for your life. Okay? Don't spend too long. But be very bold, take risk. This is the time that you can take risk. PhD is not about having a successful outcome. PhD is also about developing the fundamental understanding, irrespective of the outcome. So be prepared to go beyond the boundaries that have been specified by your seniors or by your supervisors. No, tell your supervisor, tell your senior, no, I will be doing this too. Or I don't want to do it this way. I want to investigate it this way. And then whatever you know, whatever you find out, bring it out in the open. It will still be PhD worthy. It's a philosophical contribution. It's not a $100 million producing generating product that fetches PhD. PhD is brought by your innovative thinking, what is new that you have done, what is novel that you have done, what is your own contribution. If you just follow other people's footsteps and do an incremental piece of work, that will not be PhD worthy. So I don't know how much you liked my presence, but I liked your presence quite a lot. Many thanks for putting up with me in the last 10 days. My apologies for not being able to talk to you on day 2. I was really down, but I enjoy talking to young minds such as yourselves, and that's what I did. Okay. All the best for your future. Thank you. So this is the only one that I will put. I'll put that straight away.
So you want to take video?
Yes, sir.
ठीक है, तो वीडियो ले लीजिए और you can take photo on your friends.
I have been wearing it all along.
Yeah.
If you want to come,
So Dr. Ashok Dave. Maybe you can come this side. Yeah.
let's take it again.
Yeah.
It's a left hand. Thank you. Well done.
Yeah. Yeah. Pratik. Aditya. Madhu.
Well done, Mona. Coming all the way. Spending your time with us. Thank you. Well done.
Anand.
Well done, Ahmed.
Sachin.
Thanks for all your questions. Thanks for the answers. And keep the questions coming. You never stop asking. Yes.
Rishiraj.
Enhance the quality of life for everyone.
Bridges.
Keep working on renewables for the betterment of the society. Sure.
Amrit. Moiz. Moiz is not here. Faraj. Nitesh Kumar Shahu. Nitesh is not here. Nimish.
Very good. Work hard and work smart. Yes.
Abhishek.
Never stop learning. Never stop asking.
Saurabh.
Very well done, sir. Keep your cool all the time and you always do. Well done. Well done.
So on behalf of IIT Kanpur, I would like to deliver a token of appreciation to Professor Bhattacharya.
Thank you, sir. And thanks, everyone. So, can I open it?
Yes.
Okay. So, who is going to open it for me? Anyone of? Okay. Okay. So, there are two people. Come and open.
So one girl, one, right?
Which one?
No, but Saurabh should not open because Saurabh is from IIT. Right.